You know, there's this thing that gets taught in every physics class, repeated in every science documentary, plastered on every pop science website, and well, it's not quite wrong exactly, but it's not quite right either. And the fact that everybody just says it and moves on, that bothers me. It kind of gets under my skin in the best way. They say light is both a wave and a particle, and I understand why they say it. I do. Because light does these things that look like waves, and then it does these other things that look like particles, and so somebody decided, well, let's just call it both. Problem solved. Neat, tidy, everybody go home. But here's the thing. That's not an explanation. That's just giving up and calling it a name. I mean, imagine you have a friend who sometimes acts very shy at parties and sometimes gets up and dances on the table. And somebody asks you, what's he like? And you say, oh, he's both shy and a dancer. Well, sure, technically, but you haven't told me anything about what's actually going on inside that fellow. You've just described the two things you saw him do. That's what wave-particle duality is. It's a description. It's a label. It's not the truth underneath. Now let me back up a second, because I do need to explain what we actually mean when we say wave and particle, because I think that's where the confusion really starts. When we say something is a wave, we mean it spreads out. It goes everywhere at once, kind of. Water waves don't go in a straight line. They fan out. They go around corners. They interfere with each other. Two waves can hit the same spot and cancel each other out, which is a strange and beautiful thing if you think about it. A peak meets a trough, and you get nothing. Quiet water. That's waves. When we say something is a particle, we mean it's a thing. It's here. You can point at it. It lands in one spot. It's got a location. An electron is a particle, you say. You shoot it at a screen, and it makes a little dot. One dot. Right there, a particle. Now light, when you're not looking at it too carefully, it behaves exactly like a wave. It goes around corners. It makes interference patterns. You shine it through two tiny slits, and you get this gorgeous zebra stripe pattern on the wall behind. Bright bands and dark bands alternating, which is exactly what waves do when they interfere with each other. Beautiful. But then, and here's where it gets interesting, here's where it gets kind of curious. When you try to actually detect light, when you try to catch it doing something, it always arrives as a single little jolt, a photon, one at a time, like little bullets hitting a target. Not a smooth wash of wave energy, but click, 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 one hit, then another. So people said, wave and particle. Both. Done. But wait. No. Hold on. Here's what they glossed over. Here's what I find completely astonishing. The interference pattern, those beautiful stripes, they show up even when you send the photons through one at a time. One photon, then another, then another. Each one makes a single dot, a single click. And yet, after you've sent thousands of them, the dots pile up into the interference pattern. Stripes. The same stripes you get from a wave. Now, how does a single particle, a single thing, a single click, know to avoid the dark bands? How does it know where not to land? I mean, think about that. Really think about it. There's nothing to interfere with. There's only one photon. There's no other photon to cancel it out. And yet, somehow, it knows. It lands where a wave calculation says it should. I remember a conversation I had once with a student, bright kid, very serious, and he said, Professor Feynman, so the photon splits in half and goes through both slits at once. And I said, well, no, we tried that. If you put a detector at one slit to catch half a photon, you never catch half a photon. You either catch the whole thing or nothing. It doesn't split. He stared at me for a while and then said, so what does go through both slits? And I told him the honest answer. I said, I don't know, and neither does anybody else. Not really. What goes through both slits is the probability, the chance. The wave is not a wave of light energy spreading out. It's a wave of possibility, of likelihood. The photon doesn't take one path. It takes, in some sense that we can't quite picture, all the paths that are available to it. And the ways those possibilities combine and cancel and reinforce each other, that's what determines where it finally lands. Now that's a completely different thing from saying it's a wave and a particle. That's saying it's neither. It's a new kind of thing. Something we don't have a word for yet, something that behaves in a way that has no analogy in the everyday world. And I think that's the part that gets lost when we just say wave-particle duality. It makes it sound like we mixed two familiar things together and got an answer. But the reality is far stranger and I think far more interesting than that. The reality is that this thing, this photon, this quantum of light, it's something genuinely new in the universe. Something our brains didn't evolve to picture. Something you can calculate with extraordinary precision and predict the outcome of any experiment you like, but something you cannot visualize. You cannot build a mental image of it. And I'll be honest with you, that used to frustrate me enormously. I wanted a picture. I always want a picture. Give me a little ball, give me a little arrow, give me a tiny rubber band, something I can hold in my mind. But there isn't one. There just isn't. In fact, I'd argue that whenever someone gives you a clean picture of a quantum particle, whenever they say, think of it like this, and it sounds satisfying and complete and simple, they probably lied to you a little. Not out of malice, mind you, out of love, out of the desire to explain. But the price you pay for the clean picture is that it's wrong at the edges. And in quantum mechanics, it's always the edges that matter most. What I find truly fantastic about all of this, and this is the part that keeps me up at night in the best possible way, is that the universe is not obligated to be understandable to us. It doesn't owe us an analogy. It doesn't owe us a familiar mental image just because we'd find that comfortable. The equations of quantum mechanics work. They work astonishingly well. We can predict the properties of hydrogen to 12 decimal places. We built the transistor, the laser, the MRI machine, all of it using these equations that describe things we cannot picture. That's a remarkable situation to be in. So when I hear someone say light is both a wave and a particle, I don't get angry. I get a little wistful, I suppose. Because what they're really trying to say is something true and important, which is that light is weird, that it doesn't fit the boxes we had ready for it, that it forced us to build new boxes, and even those new boxes are a bit odd and loose, and they don't quite close all the way. And I think if we just said that plainly, if we said we don't have a good analogy for this, but here is what it does, and here is how astonishingly accurately we can predict what it does, I think that would be more honest, and also, frankly, more exciting. Because admitting that the universe contains things that are genuinely beyond our intuition is not a failure of understanding. It is the beginning of it. And that, I think, is where it gets really interesting. What else is out there that we've been calling by the wrong name, that we've been pasting a familiar label onto just because we wanted to feel like we understood it? I don't know the answer to that, but I find that question completely and utterly wonderful. Utter to this to corners to this to destin a samful. Motion aloha, tu sadaration orio.